I'm a director of Explainable AI Center at KAIST, and I'm also in the graduate school of AI. And also, I found a startup company in EG and work as a CEO. So, before we briefly introduce the research outcomes, let me briefly introduce some research activity in Korea. So from 2017, South Korean government tried to spend like research fund for the big explainable AI project, and it lasts long for 5 years, and with extensive internal collaboration with DARPA and also TU Berlin and also some colleagues like Klaus, and we did some achievement. So like we were active to organize workshop in ICCV and the tutorial in ADD, and also wish to organize an explainable AI workshop in upcoming conference like ICML, and wish to invite some of you as a co-organizer or speaker and so on. So as a result, in like the last 3 years, we published a lot of paper with 200 people. And as Klaus said, Klaus is also involved in our project. And because South Korean government emphasized a lot of application with other domain like hospital and the manufacturing and the finance and the mobile like company like a neighbor and the Samsung Electronic like Bixby, we are working together with those companies, so like optimizing their process and analyzing the result with explainable AI, and also sometimes mission critical system deep neural network, how we can automatically correct and analyze and those system and so on. So and because of this, and some South Korean government agency was first to file the international standard on XAI, and as I know, many government agencies like U.S. and the EU and the South Korean government, Chinese are working together to make the first international standard on XAI. So that is actually one of the what we initiate in Korea. So, and because of this, unfortunately, like government decided to fund our project for next 5 years, including this year. So I wish to make more international collaboration with people in US and the EU and so on. That is our goal. Briefly, what we wish to do is plug and play explainable AI. So if you are working on explainable AI, then it's really like a hand manual tuned world model. As Klaus say, because deep neural network is tricky, we need to use different algorithms for different layers of the neural network. So, but what we wish to do is, as we are using the USB, like it has a standard. So if you have a new explainable like AI model come, and this plug and play explainable AI can find appropriate explanation algorithm, explanation interface, and also easy to use for the like application designer and so on is our goal. So let's get into some of the algorithm what we developed. So first question is, can you find the role of internal unit in deep neural network? So that is actually what like we discussed in the first section. And so like one of our work is explorative generative boundary aware sampling. So our goal is try to make a microscopy to see what's inside of deep neural network, individual layer, individual node, and so on. So our view is, so if we try to analyze inside, let's get into the decision boundary or generative boundary of deep neural network inside, how we can visualize, analyze, and correct, and so on is what we wish to do. That is our perspective. So there are some related work, like network dissection, as we see in the first section, and also GAN dissection that I will briefly introduce, and also Google Deep Dream, and like a relaxed decision boundary, like by work by DeepMind and so on. So network dissection is initiate from the MIT, and what we can do is for internal neural network model, so we can see which internal unit work as a classifier, object detector for part of image, and so on. So that is actually one kind of nice view. Yeah. And the other type of method is neural network verification. So like a robust deep neural network. So the view is, suppose we have a point in the input. So we are doing the perturbation in the individual axis, like we can see as a rectangle. And one of the things is, because it has a nonlinear activation, whenever we pass through individual layer, so originally rectangular shape will be changed, convex and concave shape. So our goal is, in a specific layer, we wish to check whether the point, if we perturb in the input, will pass through the critical boundary. So as you say, the safe for error and so on. So that problem is, non-convex makes this problem as MP hard problem, so very hard, but we may need to actually pursue for many mission critical systems like a medical, automobile, like a self-behaving car, and so on. So one of the people people do is try to make the polytope that include these convex and concave area, and try to verify whether polytope will violate the critical boundary and so on. But as you say that this is incomplete method, right? Because there are some area which is non-safe or classified as safe and so on, right? So convex superset may give incorrect answer for these questions. So these are, as I say, that what DeepMind proposed for the incomplete method, try to make a Lagrangian relaxed decision boundary to find the polytope. Of course, it takes a lot of time to find the polytope, and then after we find tight polytope, and try to verify whether this polytope will violate the safe critical boundary and so on. So what we propose is a little bit different method. And of course, actually, this is a probabilistically complete method based on the existing algorithm. So what we wish to do is, so based on neural network, and wish to find the specific layer and try to verify a specific example in the deep generative model, and try to see where after we perturb this deep generative model and see how the image is generated in near the area. So if you have architecture, you will have that area, and if you have a face and the celebrity, and we have this type of diverse images. And so we wish to define these as a generator G, a generated image from G, and the G is an input. And we have a hidden node H, so for example, as a fourth layer. And we have a partial generation from the G to H, and also H to the output, and so on. So we actually define that as generation from ith layer to the jth layer as G, I from J. So what we actually do is, so let's go back to basics. So most of actually machine learning model based on the linear model, right? Let's get back to the basic, and let's define this complex deep generative model as generative boundary and the generative region. So generative boundary is defined as in a specific layer, individual neuron, like a linear layer, and will be the boundary, linear boundary. If we consider only two consecutive layers, then we can define generative boundary, right? Specific unit, whether positive or negative, right? Negative becomes 0, and the positive will have some value. And we can define generative region on top of this. So in the else layer, if we have a point, and we will get the sign of individual value in the inner vector, and we can say that, so if, so all the input, all the value, generated from that, has the same sign, then we assume that they are included in the same generative region. Of course, actually, we can also define the decision region, but in here, so we concretely define generative region in terms of with respect to the sign of the value internally in a specific layer. right? For example, in A and B, so all the other vectors are same except for this line. So if we go up from this line, then we have a positive value, and we go down from this value, we'll have a negative value, and so on, right? So our goal is try to find the generated image with the same sign. So the problem, like what we define for the problem is we wish to get explorative sampling in this generative region, right? Given a GAN model, a target layer, and the input query, and we wish to find the equivalent class of the image generated from the same generative region, right? Like this. So, but we have a lot of challenge. Like the first challenge is we have too many generative boundary in a typical a neural network. So what we wish to do is, so typically if we consider all the internal layer as a critical boundary, then you consider only the small layer, so the small region. So it's too tight to consider all the decision boundaries. So what we wish to do is, so we wish to find only the important feature for the generated image in a specific point. So probably there are a lot of methods to doing this, as we discussed in the PCA or the type of a method. But in here, so we use the smallest supporting generative boundary set from the paper in here. So what we are doing is we are using Bernoulli mask optimization to relax the boundaries. So what we wish to do is we wish to minimize number of activation, but only the activated unit survive. The generated outcome is like a minimum distance with the original image that generated, right? So this is a typical example. If you only try to getting the point red, and if you visualize all the internal decision boundary, it's really complex. But if you only use 10%, and we can use as we have in the middle image, and if you use only 5% and the right image, and so on. So we are using this one to reduce the complexity of our visualization. And another one is actually generative region. Sampling in the generative region is very challenging, as we discussed in the NP-hard problem, like a concave or convex shape. And so we have a lot of dimension, and also we have this non-convex set. So what we can do is, so if we have a generative region in the original one, so we actually apply our Bernoulli mask for the smallest supporting set. So that is actually what we in the a second figure. But if we apply the conventional method to search this complex area, epsilon-based sampling for the area for the very small area, then we have some area which is blind area. And if we use the big epsilon, and we are getting the out of vision area. But if we actually sample in the internal deep neural network, so what we found is actually epsilon size does change over a different region, different layer, and different a feature, different node may have different size of epsilon. That is also a very hard problem to solve. So this is one of the examples that we actually visualize. For example, in the so these individual figures are pointed at a different color. So as the layer go deeper, as we can see that, so complex decision boundary typically seems from the linear become as very complex nonlinear shapes, as we see. So what we try to do is we are trying to solve this problem by reduction of this search problem by robot planning problem. So in the robot planning, so there are a lot of complex, non-complex shape, and people try to solve this problem by connecting different configuration. And so we reduce the sampling problem into the robot planning problem and use the algorithm called RRT. And we build generative boundary based rapidly exploring random tree algorithm. So from like a sample, so we are trying to explore our, like expand our tree and searching this actually path, and whenever we meet the decision boundary and we stop. And one of the good things for the RRT algorithm is it is probabilistically complete. So if you have a lot of time, then you will always find a small like hole with a probabilistic like complete sense. So you can search through the algorithm and find the reason. So these are our algorithms. So if we have a deep generative model and we have a latent point and we only find the important boundary and apply the RRT algorithm and compare our result. If you have a query image and compare to the epsilon-based sampling, and also it is very hard to find epsilon, but this RRT algorithm is actually much flexible to find these internal area. So these are examples that we find. So we eliminate some of the internal decision boundary, but we can clearly see if we try to expand from the green direction and the blue direction and the like orange direction and so on. So the blue one is on top, and the yellow and the like orange direction and also green direction. So can you see the difference between the green and the other part? Yeah, so hint is in this part. So window, right? So probably there is some like a decision boundary for the window to actually visualize. So because we reached some of the decision boundary to visualize, so we can see that. And also if we compare this actually blue one, the other, and if we concentrate on the background, then the color would be in the blue was more grayish than the like other part, the yellowish and so on. So then we can also know that there would be some internal decision boundary, which is less important than the architecture and the other feature, but like we have some hierarchy. So we can see these paths will like visualize where the like change is happening. So if we compare with MNIST data set, then if we search through the same volume, then compared to the epsilon-based sampling, we actually see that the context of the query maintained, and also building architecture, and also scalability feature, and so on. And we also did some experiment on the number of decision boundary that we keep for this experiment. So suppose that, so in a specific architecture, so if we only use 10%, more than 10% of decision boundary, the generative image is in the left column. And if we use less than 10%, and the generative image is in the middle, and if we use less than 5%, the generative image is like this. So you can say that so most of context is maintained if we use more than 10%. Of course, important 10%, like based on our Bernoulli mask optimization. And also the less than 10%, we can see that some glass is happening. So we can also identify which decision boundary making this glass. And also gender seems to change. And of course in here, the color and the shape change more. And if it's less than 5%, then the architecture shape and the background change more and the gender. But we can see that the shape, so the way they are looking at, and their hair color, and also their jacket is maintained. So we can see that by eliminating the less important feature, then we can see which feature are regarded as important for this deep generative model and so on. So that is actually what we can do. And so we have a following question. So we can try to analyze within like a decision boundary work in which sense and how these manifold and the search and so on. But so the next questions are: can you find internal unit which behave badly, making artifact in deep neural network? And can you control internal unit which behave badly to make the better result in deep neural network is our following question. So I start with the GAN dissection. I'm really big fan of LRP algorithm and also network dissection and GAN dissection inspire me a lot. And again, what GAN dissection research do is let's try to find which individual unit make with the individual object. And what they try to do is based on feature map and given the generative image, semantic segmentation, and when there are a lot of mean intersection of union, then they find probably the feature map making the tree shape and so on. So we already see the example in the first talk. And so in the church example, the unit 109 making tree and a unit 32 making dome, and if we try to compare, overlap the image with the specific activation part and the unit 32 and 109, we can know this. And the dining room samples, and we can also find which part is window and which part is table and so on. So this is the interesting part. But actually David said is, so somehow they find some image with artifacts. So because we already know that generative model has a lot of cherry picking, meaning that so during the generation process, so there are a lot of artifact image and not so robust image, but people emphasize well-generated image and so on. So but what they say is, so some of the image that generated from the model has this part, right? And they find the individual unit and unit 63 and 231. Whenever they are activated, this shape is generated. Probably, I think that try to make the curtain. The curtain is hard to generate, probably. And so what they said is they manually find this and eliminate. And the images are correctly generated. So from the image with the artifact, and when we find which unit make this artifact, and we can correct the image with a better improve the result and so on. Right. So we are trying to do this for little automatic fashion. So meaning that because previously they use FID score and so on, but somehow the result is not fully automated and so on. What we wish to understand why, when this artifact image is generated and so on. So our method is relatively simple. We call sequential correction. So what we try to do is, this is a supervised method. So generate a lot of image from the generative model, and we label whether this image has artifact or not. So we try in a classifier whether to identify whether this image include an artifact inside or not. So we use this, and we use a supervised method to train this. And we use GradCam whenever artifact is generated outcome, and we ask where it is in terms of GradCam. And so with this GradCam mask, so GradCam mask will give us which part is weird, right? And so on. So then we can find the unit sequentially from individual layer and try to find when there is a big overlap between the GradCam mask and the internal activation, and we are turning off their activation. So simple, right? So these are our results. So if we try to compare with FID and the other like existing method, and if we compare our sequential mask, then our sequential mask gives this is the original image, and the fourth column is our result. And to see the many of image which is not like correctly correctly generated will be like improved by our method and so on. Yeah, so these are some of the results. So sometimes, so if one of dirty, bad like shape is clearly generated, clearly like corrected, and the sum of the image which is like shadow, like overlap, is generated like improved, and like a not so well like generated image also improved and so on. So like a cap, like improved, and some part in the mouth is like improved and so on. So these are, as Klaus say, shameless advertisement, and our method is advertised by one of the like blogger in US, and they say that so South Korea is very famous for the plastic surgery, and we didn't say anything in our paper as plastic surgery, but the blogger say that this is plastic surgery for GAN-generated face, because South Korea loves to do plastic surgery. They're even doing for the GAN-generated face and so on, is actually what we do. And this is selected as one of KAIST breakthrough that I'm working on as automatic correction of internal unit in generative neural network. So, like, of course, our work is inspired by GAN dissection, but we are trying to make this process more like semi-automatic, and it's what we are trying to do. There are some observations that we did a lot of internal investigation and to analyze deep neural networks. We did a lot of like experiments. For example, when and why those artifacts is generated. Sometimes what we observe that is actually if we try to get the interpolation between two internal unit and the point, vector point, and some of the way that we move actually the matter sometimes. So the red one, this part, like make more like a artifact which part is generated, and blue is not. And also you can compare, like clearly see, even if there is not that big difference between one position to the other, we rotate our face, and this blue path give us more clear artifact, like shadow, like shape. So like the thing is, whenever there is some like part, even if very small, then there is actually this type of artifact generation part, then we are very hard to avoid this actually like a location to generate this like artifacts include image and so on. And also another like issue is it depends on the like a data set. When we visualize the value of the generative model, the value higher is close to the real image, lower is close to the like fake image and so on. But so if we try to visualize, there are sometimes like a big mountain and so on. So we investigate this. And the reason why we generate sample in this part, which is higher the value, looks like real sample, and around the area, like this is like a big clip-like area. And what we analyze, we understand that is all the sample inside has a caption, because real image has a caption. Whenever the image is not looks like real, if we have a caption that it has higher TP, like a D value and so on, the other part is more like a real. So like we also has this type of like still like a thing to improve in the deep generative model. And this is what we can see. So, and in the same image, so if we try to move and see the generative result, and suddenly the value steep increase when the caption is generated from left to the right and so on. So watermark. So our previous method seems to work. Of course, there are a lot of things to do more further, but the one thing is, so our previous method should is based on the supervised learning, meaning that so we let the generative model generate a lot of sample, and the human need to label whether this is artifact or not, and so on. But that is actually our original question that we used to solve, but we solve in the opposite direction. But somehow, so can we do this for the unsupervised way? And because we have a labeled data, so we can try to find the feature and so on. So of course, that is not completely done. So we are seeing only part of this, but we're trying to share some of the result. And yeah, so one of the work is try to see this. So our hypothesis in here is, so locally activated neuron seems weird. So a locally activated neuron may be unstable to generate artifact, meaning that, so if we have a G value, so G value from axis 1 to 100 and so on, so we are trying to find the one internal unit in a specific location, right? And we are perturbing our individual unit in the 399 and 151, and perturbing this when this activation is suddenly picked in a small spatial area in the manifold. Probably that seems weird. So what we actually hypothesize, we conjecture is probably that try to generate something, and that is that is prevented by the gradient descent algorithm from the generative model, a discriminant value, and try to make something and squeeze, but it doesn't go away. Somehow survived, right? That is our hypothesis, conjecture. But anyway, so whenever there is a very sharp activation in the small area, let's try to see what's going on. So these are our comparison. So this is a generative unit. Whenever it is activated, the leap is made. And this 179 is the a unit that generates the background as a red, all red. And let's try to see, so this all red one in a specific area in each axis. Then what we can see is, so at least for this a specific sample, whenever we perturb a little bit, and the sharp peak is generated. But all the legitimate sample, legitimate feature, their activation is smooth, as you can see. So when we change this feature, the activation is going smoothly, go up and down for the direction that we generated. So our hypothesis is, whenever this is generated, then we regard as bad one. And whenever this is actually smooth activation, then that is a good one. So our hypothesis is to make our outcome generated from the generative model is more robust, without including the artifact and so on. So we define this as a curvature of local activation, but seems complex, but the notion is very simple. So in a specific location, we are trying to perturb, and the activation goes down, right? So sometimes goes like a stable and so on. So we are finding the change point in terms of, you can think about time series analysis. Whenever there is a change point, we put a point, and we have a point in the middle, and with a point in the change point, and we are trying to approximate these 3 points with the quadratic approximation to find the curvature, right? Whenever this curvature is big, then we can say that there is a local activation. When a curvature is smooth in terms of these 3 points, or this is an approximation and the heuristic approximation, and we can say that this is a good unit, and so on. So we are averaging them for all the activation unit in the G and the specific area and so on, and we are comparing and divide, that is the sample with most of low curvature local activation, or sample with at least some high curvature activation. You can clearly see that the left-hand side, which is most of the activation are low curvature and smooth, and then they are more stable and without like a few artifacts and so on. But if we include at least some high curvature, like a high local curvature, you can see that there are a lot of like artifacts generated and so on. So of course, actually, we didn't know why actually this is happening during the learning procedure yet. But somehow you can think this is a kind of result to try to like eliminate those artifacts. And the sample with the low like curvature in the car and the cat, and also high like curvature in the car and cat, and we can see that. But one thing that we can note in here is, so we are trying to say artifact is bad, but somehow the like sample with high curvature has a more diverse shape and the perspective and feature and color and so on. So what we are trying to think, like we are trying to understand the result is probably deep generative model try to make diverse new thing in the individual feature, but they fail to do in the like a low like a local activation, like high local activation and so on. So that is actually what we are we understand. So we can clearly see that, so like measure in RS and the PPL, so RS better, like a higher is better and the PPL low is better. And we can say the low, like a local curvature, like a method is more like stable, the better result than the high curvature in terms of image fidelity and so on. So this is also what we can see. So if we try to make the high, like a local curvature, like image with a high local curvature and find those unit and eliminate it, and correctly result, as we can see in the previous one, and also improve in terms of image fidelity and so on. So there is one. So like one message that we say that probably local activation is too spiky in a specific area, then we can think actually that makes some artifact and so on. And we try to do other like observation inside. One of the things is this one. So previously what we discussed is, so local activation, shape of local activation does matter to find or contribute to the artifact. So how about the like frequency of activation? So probably the neuron, which is rarely activated because of lack of training data or not so frequently occurred feature, would be less stable than the like a more general feature and so on. So that is actually like our hypothesis. Rarely activated neuron are used to create diverse component, but sometimes would fail to like generate one. And also frequently activated neuron are used to construct general component, and probably they have a more chance to be trained, right? So what we actually like compare is, because we know that artifact image and the normal image and so on, so we compare in terms of like a number of, like in terms of individual unit, so in terms of number of activation patterns. So the activation rate in the left-hand side is less activated one. The right-hand side is like a more activated one. So if we compare the less activated one part, then we can see that the ratio of artifact is higher than the normal. And also one in the like more activated part, then the normal is more higher than the like artifact. That is actually makes sense in terms of training, right? So, and we can see that these part, like artifact part, is concentrated on more on less activated unit. How much time? Okay, yeah, so that's good. So if we compare, then if we have a few less activated neuron, then the image is diverse but not so have a lot of artifact. But if we have an image with many low activated neuron, then we can see that a lot of artifact is generated and so on. So we can clearly see, so for some like a sequential, as we say, the sequential ablation, we can try to eliminate some low activation from the lowest activation to the higher and so on. So then we can also like correct. So somehow, and we can also see the fidelity is also improved. So yep, so you can see that these images are improved and so on. So like a defect part in artifact image were corrected by our method and so on. Yep. Yep. So in here, so that is not conclusion, but somehow I wish to share it. So whenever we actually eliminate those units which make artifact, we observe that the generated result is simpler. And the shape and the perspective and color and the background is like less diverse. So the thing is, probably our like way of learning, training the deep generative model should be changed somehow to concentrate more on to make diverse feature, creative feature, like sometimes try to make a new thing, making failure like artifact, but somehow like our way to go is not only like eliminating those methods, how we can correct and how we can make those methods more like diversely trained for the generative model either way. And we are also concentrating that part to make model diverse and also concrete and so on. So these are like a remaining part that I wish to like share. So I'm working on a lot of time series data analysis and working for many industrial application, healthcare, and factory optimization and so on. So we recently making some method for explainable AI method for time series model. So as we discussed in the previous section, then one of the big issue compared to the image explanation, then the temporal time series like explanation is the lack of the training data, like semantic segmentation label. So in terms of image, we have a lot of training example for like which part is like hand, which part is face, and so on. But in terms of time series data, even if we have some open data set like UCR, but the semantic label is like sparse, and we don't have a lot of semantic labels. So what we try to do is, so based on training the time series data and try to understand individual unit, so which type of input is come and which like this specific individual unit is activated. And we use clustering method and find the prototype, and we overlap the representative example as a prototype and overlap to the input time series data. And we can see that, so based on the prototype, the input is a little bit spiky earlier. And also we can see that based on the prototype, this example is like going up and down a little bit later, and so on. So one of what we make in this is value LRP plot. So this is time series value, and this is LRP value in the y-axis. The reason why we need this type of one is, so we apply LRP to the time series data, and typically the time series data give the color, right? Red color with like a more dark red and the light red and so on. But it is very hard to see which B and which A is darker, higher, bigger, important. And if we compare with the value LRP, and the value is how the value is lower and higher and so on, so we can completely see that this part A is bigger, twice bigger, like LRP value, and also see that C, D seems like bigger, like LRP value when we compare with the value LRP, and the C value in here does not have a lot like bigger LRP value and so on. We can clearly see with the one eye value LRP plot, and that is actually what we made, and compare these are these are like a typical pattern of value NLP, and these color are pattern that activated in this specific type of the scenario and so on. So this is my final part of the presentation. So one of the fundamental questions, there are some questions, but one of the fundamental questions to explainable AI in terms of deep neural network is how we can improve the attribution method, the specific attribution method, so called the integrate gradient. So of course there are a lot of open questions like base value and how we can find the path and so on. But like a key question that we are trying to achieve is, so based on the path, which path we are moving, our value different. So these are like a work that we recently presented in the Generative. And I will try to only explain the intuition. So in the integrate gradient, like integrate path gradient, and we are assuming that there is a base point, meaning that, so if we try to find the curve, the image with this curve is our interest of input attribution, but base value is this image. The same image, but the curve is disappear, right? Base value. So typically it is very hard to semantically find these base values. So what people do is the black, like a screen, like black value is base value, other type of the mean value is base value, and so on. But anyway, what we try to do is, suppose the x hat, like x bar, is our base value. So the green part is our real input image. Then we are trying to improving increasing this value to the the part in the original image and try to find how individual paths and how the attribution change, right? So that is actually what people try to do, but depends on based on our experiment and the analysis. So we are based more on the decision boundary. What we know that is, so attribution does not change much inside of the decision boundary, right? So the attribution that we compute in here in individual region should be similar, right? But in a real method, we are trying to make noise generation and so on. It does change a lot, right? What we know that is, the input attribution should change like the stair, right? Because it depends on our decision boundary method and so on. So what we try to do is, so that is actually like a pathology. So if we try to add the noise and so on, right? So then some part, like a full gradient, the result with generated the noise and this full gradient that change a lot in terms of input gradient. So what we say is it doesn't need to change much. So when we travel the path. So this is our a result what we wish to get. And so one of the a method the heuristic trick that we actually apply is, so based on our assumption, probably most of the important and input attribution while we are traveling the path may not in the very small change or very big change. One thing is, so even if there are some a small change in the input attribution, probably most of them are noise. So what we do is we do filtering. When the input attribution is very small area, so small area, then we ignore them. So we ignore them as a 0. And this is the result. So from the image with the black, and from the original image, while we are traveling the path, and whenever there is actually small change in the input attribution result, and we ignore. And another one is, that is actually still what we may need to go further. So if you remember our spiky local activation and so on, somehow, so suppose that we are finding the relevant feature here from the base point, we are traveling, but somehow the non-relevant feature for us, but relevant feature for the other feature appear, then probably, so the our activation for some part is a spikily, locally activated and so on. So we ignore these change and put that as 0 value. So the one of the example is this. So when we try to ask, where is the instrument, but somehow not only for the instrument, so face of person is appear suddenly. We can see that. So like instead of this part, like face of attribution of face is increasing further, more, and so on. So that is happening in the very small area, probably for the other important part, and also we ignore the top some percent of intermean activation through the path. So our algorithm work is like a local activation and the mask extraction. Mask extraction includes the filtering of the small value, filtering of large value. So justification is that I say, and so then we keep doing these as traveling the path. And so we have attribution and the mask, and based on the mask of image, and we are doing the activation, attribution, and also based on the mask and also mask of image and the attribution computing and so on, integrating this is our final input attribution. So that is very similar to the somehow integrate gradient, what Google typically love to do, but our method use these two filtering methods. Yep. So we compare this result, and the guided integrate gradient is what Google typically provide in the TensorFlow package, and the full gradient and our method is compared. And so we compare with the leave relevant first, least relevant first, meaning that we are eliminating pixel with the least relevant one, and we are eliminating the pixel with the most relevant one. So if we eliminating the pixel, we are making all the individual algorithm, making the order most relevant one is eliminated, and our accuracy should drop first. And the least accurate one is eliminated, our accuracy should drop last, and so on. And we can see that, so our method for the least important and the most relevant method, and our method is better than the guided integral gradient and full gradient and the other gradient-based method and so on. Right. So yeah, so that confirms the result. So of course, actually, in this type of research, we need to analyze theoretically or empirically and model-wise further. But what we are trying to do is we are trying to understand the insight, how we can make the input attribution method more. So as I say that I found my company, and working with many industrial partner, and they say that why various explainable AI method give different output? Can you explain why? Why input gradient and LRP and also gradient times input give us different result? And can you explain? And so on. Of course, there are a lot of issues like a base point, and also as Klaus said that the pooling method does not give an inverse, exact inverse value and so on. But somehow, improving this one is very important one for everyone. So in the workshop. So I try to conclude with my talk is, so my company is trying to predict how these automated factory procedure work, and the one of the important feature is to explain when individual input value or control value contribute to the final outcome and so on, and many customers really love to see and love to operate with this explainable AI method. Of course, they have a complaint and they have some doubt whether the provided output is really a correct one. And we are applying this to manufacturing result, and working with many partners in Korea and Japan and so on. Yep, thank you.